I bet you've heard that the sun is 93 million miles away, that the Andromeda Galaxy is 2.5 million light years away, but I'm sure you know we have no measuring tapes that long. So how do we know this? Well, we've actually never had a single reliable method to measure all distances in space, but astronomers have built a set of successive methods known as the cosmic distance ladder to measure farther and farther out into the universe. Stan is going to climb this ladder with us. We start with our local realm. Kepler derived his law that relates period to orbital radius, allowing astronomers to measure the distances from other planets to the sun in relation to Earth's distance to the sun, which we call the astronomical unit, or AU. But they never actually knew how large the AU was. The comet guy Halley used a fascinating method to quantify it: Venus's transit across the sun. When Venus transits across the sun in Earth's field of view, two Earthlings at different latitudes separated by a distance h will observe two different paths of Venus's transit at different times. The angle theta between these two paths is equivalent to the angle theta between the two positions of our Earthlings. The tangent of half of theta is equal to half of h divided by the distance from Earth to Venus d, which allows us to solve for d. My boy Kepler showed that the Venus-Sun distance is 72% of the Earth-Sun distance, so the Venus-Earth distance is 28% of the Earth-Sun distance. 93 million miles. Isn't geometry just gorgeous? Now that we've seen how the AU is calculated, let's get out of our solar system. What we just did with Venus actually involved the concept of parallax, or the shift in the observed position of an object that occurs when you view that object from two different points. As an example, hold your thumb directly outwards from your body. Close one eye and observe it. Now do the same with the other eye. Alternate between your two eyes and you will see your thumb shifting in position. Now extend this example to our solar system. Your thumb is a star, your nose is the sun, and your two eyes are Earth at opposite points in its orbit. With some trig, we can find the distance to the star based on that positional shift, the parallax angle, and the astronomical unit. And notice how when you're driving, distant objects have little change in position, whereas nearby objects whiz by. In the same way, because the stars are so far away, the parallax angle will be extremely tiny. In fact, astronomers use tiny units for degrees called arc minutes, which are a 60th of a degree, and arc seconds, which are a 60th of an arc minute, or 3600th of a degree. Check out the distance when the parallax angle is 1 arc second. This measurement is called a parsec, or the distance measured when the parallax angle is 1 arc second. Our distance formula can now be modified to 1 over theta, where theta is in arc seconds to give us answers in parsecs. Although parallax is beautifully simple and useful, it's difficult to measure a parallax angle smaller than 1,000th of a degree. Past 5,000 parsecs, parallax becomes unreliable. But hey, we're already 20,000 light years in. Let's climb past direct geometric measurements to standard candles. To understand them, we'll need some background. Astronomers label the brightness of objects with a weird magnitude scale, in which lower magnitudes represent brighter objects, while higher magnitudes represent dimmer ones. Since the magnitudes shown here are measured on Earth, we call it apparent magnitude, and it'll change based on an object's real brightness and its distance from us. But to set up an even playing field to compare brightnesses without the effects of distance, we also use another type of magnitude called the absolute magnitude, or the magnitude any object would have from a fixed distance of 10 parsecs. Using the inverse square law, or the concept that light radiates in all directions in an expanding sphere from a star, the apparent and absolute magnitude can give us the distance to any star in parsecs. You can pause for a complete derivation, but this is called the distance modulus. Since we directly measure apparent magnitude from Earth, that piece of the puzzle is easy. The issue is absolute magnitude. Fortunately, Henrietta Leavitt noticed something with Cepheid variable stars. These monsters vary in brightness through pulsation. A cycle near a star's death where it expands and contracts due to a battle between gravity and thermal pressure. She saw that the longer the cycle pulsation was, the brighter the Cepheid variables were. Since the ones she observed were all about the same distance from us, she knew that differences in the actual luminosities between them caused the differences in brightness she observed. Think back now, remember that absolute magnitude, not apparent, represents the actual luminosities of stars. Henrietta was so clever that she figured if she could first establish this direct relationship between the time of pulsation and the star's real brightness, or absolute magnitude, she could then find the absolute magnitude of any Cepheid out there simply by observing its period. She established this period-luminosity relation through calibration with nearby Cepheids that we already know the distance to with parallax. Once you have the absolute and apparent magnitude of any star, you can find its distance. Cepheids are so bright that they help us measure distances of up to 1 billion light years to other galaxies. But our universe is so huge that eventually Cepheids aren't bright enough. However, type 1a supernova all have a set peak absolute magnitude of -19. So as long as we can measure their apparent magnitude from Earth, we can find the distance to them easily. Now we just have one more important step to climb. While observing the spectra of light from distant galaxies, the brilliant man Edwin Hubble saw that the wavelength of that light was shifted. This phenomenon occurs when an object is either approaching or receding away from you. When approaching, the relative motion causes the wavelength of light to decrease and shift to the blue shorter wavelength side of the spectrum, or blue shift for short. When receding, the opposite happens and the light undergoes redshift. Apart from galaxies under mutual gravitational attraction, Hubble observed that almost every galaxy spectrum exhibited redshift. In other words, galaxies are all moving away from each other. Aha! The universe, space itself, is expanding. From the redshift, Hubble was able to calculate the recessional velocities of these galaxies. With the galaxies he knew the distance to using Cepheid variables, he realized something. The greater their distance from us, the greater the recessional velocities. Similar to the period-luminosity relation, he was able to calibrate the relationship between these two parameters, the Hubble constant. With the recessional velocity of a galaxy and the Hubble constant, you can calculate the distance to it. This rung of our ladder measures distances on the scale of the entire observable universe. Unfortunately, it's been difficult for astronomers to establish an exact value for the Hubble constant, and it even changes over time. Speaking of time, Hubble's law has enormous applications in cosmology, or the evolution of our universe. In fact, let's get a sneak peek. Hubble's law shows us that galaxies have receded a certain distance from each other with a certain velocity. We can express this velocity in terms of that distance, and the time it took to recede that distance. D cancels, and we can solve for time with Hubble's constant. Since this is the time it took for galaxies to expand to where they are now in the universe, it's essentially the time from the Big Bang until now. In other words, the age of the universe. This is the end of our cosmic journey. Wrap your head around the fact that we humans, flawed biological creatures, have come this far, have measured the immeasurable, have understood the incomprehensible, and have begun to get a sense of this dark but exciting place in which we live, and our place in it. Thanks for watching.